Hi, thanks for having me. Yeah, I did. I guess it was last year I did the Taito F2 core. Um, and yeah, I think the last time we talked was after the IRM M92 stuff, which is probably a few years ago now at this point. Which it seems sometimes it seems just like yesterday, and then other times it seems like years. I think I've been involved in mystery now for I think 6 years was was my first kind of like code submit um, to the MiSTer project, and it really doesn't feel like it's been that long. Yeah, like I'm a software developer by trade. I've been working in software for like 25 years. So hardware is pretty new to me. Um, I may have told this story before, but I started when I started university. I was doing computer engineering. Was the course I was doing, and I switched to computer science after my first year. And I can vividly remember being in a lab and like some electronic circuit I was working on was not working, and the lab assistant came over and like said, "Oh, just put a capacitor there." And I was like, What exact value of capacitor?" He was like, "Oh, it doesn't really matter. It'll just stick a capacitor there." And then I realized that like electronics was this like you know, deeply like scientific engineering discipline that also had this like, piece of magic related to it as well, where there seemed to be a lot of like feel and intuition over how things work. Like now, of course, I understand what decoupling capacitors are and why the value didn't really matter all that much in that situation. But I pretty much abandoned electronics for like 20 years of my life, and then came back to it as kind of part of this FPGA stuff.
Sorry, because you can hear me, but people couldn't. Now they can hear me. I'm terribly sorry about that. And yeah, my microphone was wrong, but the important thing here is Martin, not myself. So that's all cool. And and yeah, so first question regarding this is you made Taito F2 last year, right? And
Mhm.
why not Taito F3?
Um, F3 is definitely more complicated. It's been a while since I looked at the specs, but there was like it's got a sound processor that doesn't exist yet as part of an FPGA core. I think it's like 6820 based instead of 68,000. Though I'm not 100% sure on that. I can look up
Yes,
this.
yeah, I believe you're right.
Um, there was just a whole bunch of stuff where like it was I need like I need like kind of like to be able to understand how I'll get from A to B to C to D in a project. So I need kind of like it to have like small steps I can take.
Yeah.
And if I sit down and look and like there's a whole bunch of chips that aren't implemented,
Oh, I see.
um, it's super daunting to me. Um, but the F2 it has like with 68,000 base, so there's like a pretty solid FPGA implementation for that. It's got a Z80. It had a sound processor that Hotego had already done a version for. So it just seemed achievable, and it also the way the system is built. It's kind of like F2 is kind of interesting because it's a two board system.
Yes.
They made single board versions too of certain games, but it's two board system, and the main board um, it contains like a bunch of RAM because it uses a frame buffer for the sprites. It contains the Z80 and the 68,000 and all the system memory, and it contains the two like the sprite and the tile map hardware, and it contains the sound hardware, and then all of the actual like that's it for the main board. Then the game boards themselves contain like the ROMs, but they also contain all the video output and audio output hardware. Like the JAMA Edge is actually on the game board, not on the main motherboard. So it's a system that starts off kind of simple because the earlier games just use the kind of hardware that's on the motherboard, and then later games get more and more advanced and use additional hardware on the game boards themselves. So like, Final Blow is kind of just like it just uses all the base hardware. But then you look at a game like Dead Connection, and it has a whole bunch of, it's got different tile map hardware. It's got those games that have like rotation and scaling hardware. So it looked, as a system, it was like I can sit down, I can build a core that will run Final Blow and solve like 50% of the hardware in the system, and then each game was kind of like adding additional variations on top of that. So it was like a progression from the first game to, I think the last game I did was like Dead Connection or something, which is a much more complicated system. So I could sit down and look at it and say like I can take all these baby steps to get from nothing to multiple games working.
Yeah, that makes a lot of sense. And now regarding PGM, many people compare it to Neo Geo. How do you feel about that?
I mean, like it does seem very similar. Like it is it's a cartridge-based system. It's got a 68,000 CPU and a Z80 for audio. It's got a ton of it's really designed around pushing sprites. Like the Neo Geo doesn't even have like tile map hardware except for the text overlay display, I think. This system is very similar. It has a background tile map layer, but it's not used that heavily by games. Like games generally use sprites for almost everything on screen. Very similar to the Neo Geo in that regard. So I've heard some people refer to it as like the Neo Geo successor or like Neo Geo 2, but it's it's not powerful enough to really to be considered that. I think if it had a more powerful CPU, it could probably do a lot more. Like you look at later games like Demon Front that generally use there's like an ARM CPU on the cartridge that they use, and I feel like if they'd waited maybe a year or two, they probably could have done something like put an ARM CPU on the main board itself. Like it's most of the games ended up shipping with an ARM CPU on the cartridge just to make up for, not necessarily to make up for the deficiency of the 68,000, but eventually they did use them in that way.
I see. So regarding that, we'll talk about this PCB architecture and the cards that you just mentioned. This one does have an ARM CPU, right? And it's that one there, right? I believe.
Yeah, what game is that?
This is the Guardian. The Gladiator, sorry, the Gladiator, yeah. Yeah, I believe this, well, I'm sure this one has an ARM CPU because we had to dump the internal code for this one and it was encrypted. So we had to do some hijacking of the BIOS and just dump it from the screen back in the day. But what are those CPUs used for then?
On the main board, there's it's actually a pretty simple system. When you have like I think probably like maybe 60 to 70% of arcade games are like a 68,000 as the main CPU, a Z80 for audio, some audio chip. In this case, it's a pretty unique one in the Wavefront ICS chip. But that like 68,000 Z80 like combo is like covers a huge amount of games, and it's the same thing on the F2. And actually, when I started working on the PGM core, I just took the F2 core and used that as a base because again, it's like 68,000 Z80. The first thing I got running was just kind of get the BIOS running to a point where I can at least see it executing code, and that was just on a heavily modified F2 core that I got that running on.
Oh, nice. Nice that you use the F2 core as a basis.
I mean, like I said, like I need these kind of baby steps to convince myself to.
I fully understand.
Work on a project. So the fact that I could get it like running, and I could see it printing, I could see it trying to print an error message to the tile map memory. And that was just like an afternoon of work. Like, can I take these ROMs from the BIOS and run them on the F2? And that sent me down this road. But on the system itself, it's got like the main. There's like the what is it? Is it the 26? The IGS 20? The IGS 23 is the main graphics processor, and it does all the sprites and all the tile maps. It supports like 256 sprites. They can all be pretty large. They have scaling, zoom up and zoom down. They are 32 color. I can't remember how many colors there are. I think it's a 32 color, and
yeah, 32 colors each. Yes.
Yeah, those are used for almost everything. It also has a tile map layer. During the development of the core, we actually discovered that the tile map layer supports scaling.
Yeah, I saw that, but it's never used, right?
I haven't found a game that used it. For like MAME, for years assumed that there's like these scaling bit masks you set up, and MAME for years assumed they were used for the sprites. But then when I started running tests against it, like it was having no effect on sprites, and then I realized it was actually scaling the tile maps. But it looks kind of broken. Like certain scale levels don't work correctly. It doesn't seem to really support like smooth. Like you can't really get like a smooth scaling effect. Like I imagine games just tried to use it and then realized it's easier just to do this with sprites.
I see. And regarding, you just mentioned MAME, and it's obvious that it's the main reference for many of us as repair PCBs, many of you that do development, because they've documented this for years and years, and they have an architecture to just like you said, you have some parts and you keep on adding on them and just check the memory maps, right? And obviously there are some things that are not documented in MAME because they don't need them, right? They can have some abstraction, as we talked, like, I don't know, the PLDs here, right? They probably are never documented or used in MAME. And do you use them in the core? And second, what is your relationship with the MAME people? Do you have any?
So yeah, like MAME has the ability to I don't want to say it takes shortcuts, but there's things it doesn't have to care about. Like it doesn't really have to care about like how does, video memory is shared between the CPU and the IGS 23 processor, and MAME doesn't have to care really about how that relationship is managed. But for an FPGA core, like I need to work out like what system controls access to that memory, and then what impact does that memory access have on the performance of the CPU or the graphics processor.
Yes.
But like MAME is like an invaluable reference, especially for things like memory maps. Like where are these devices located? What kind of data format are they expecting? Stuff like that. It's just like having MAME there for all this information is super useful. And I'm like there's a bunch of changes I want to push back to the MAME implementation of this, especially around the sound processor and a few things around the graphics one too. Just because they're I don't see it like whenever I mention like MAME not being accurate or MAME not having like correct information about stuff, it's really not a criticism because I wouldn't be able to do anything I do without having MAME as a starting point for a lot of these things. Like just if all MAME did was document like the memory map, like that is in itself invaluable. But it's got a lot more. And I use a combination of like MAME as a reference, I use hardware as a reference, and I try to set up my development environment so I can easily kind of build tests that I can run on real hardware, I can run on the core, and I can run on MAME. I can compare against all three of those whenever I need to do things. Because obviously, running something on MAME is a lot quicker than building it and running it in the core or running it on real hardware.
Yeah, of course, and if you know the limitations and I mean limitations just as you said, because they don't have to. You have an abstraction and you're running using the computer hardware, you're using the host hardware for video, for memory copy, all that stuff. Your target is that, and it would be way slower if you did it in some other abstraction way, and you gained nothing in software
Yeah.
emulation, right? So yeah, I've also, I mean, not at your level, of course, but I've used MAME debugger, and it's a lifesaver in many situations. But obviously, if you don't have access to the hardware, it can also be a deadly trap, right? Because sometimes you do something and it works in MAME, but doesn't work in hardware. That was never the intention. It helps enormously, but sometimes you find yourself with stuff that works in your emulator but doesn't work on real hardware.
Yeah, I'm always like whenever I'm starting, like what I like to do is like I like to write test ROMs that I can then run on real hardware, and like it's always interesting the first time you do that because you'll build something and then it will work in MAME, and then you'll go try to run it on real hardware and you just get a black screen. And usually that's because there's some like reset that needs to happen, or there's some like register value that needs to be written on the graphics processor or on something else that
Timing, right?
MAME needs to worry about, because every game does it and then they never have to worry about it again. And then it doesn't matter in MAME if you do or do not set that value. So there'll usually be like an hour or two of frustration where you're just kind of like, it's still a black screen, it's still a black screen, it's still a black screen, and you're like working out what is the missing step I'm doing. And in that case, I'll often like run a game in MAME and look at what it's reading and writing to, and see if there's some area of memory or something it's doing that MAME just doesn't care about, that I can then like emulate the same thing in the test I'm building and eventually get to a point where something appears on screen. Like I built like this thing for the PGM. This like slots into, the kind of like the cartridge bus is kind of like 4 separate connectors. And the top right one there that's kind of like where the program ROM runs from. The bottom layer of these connectors are like Sprite and music data, and then the top left one is tile map data. So this thing I built just to go into the program ROM thing, so I can just write program ROM code. And because the BIOS has tile map data and it has music data, like I can reuse that as part of testing. But being able to rewrite program ROM super quickly and like run through stuff like that has been like super valuable.
That's awesome. Yeah, so now that you mentioned that, and you mentioned that some of the code runs on the ARM CPUs, does that connector also have that communication?
Yeah, so there's a bunch of signals on there. There's enough to, like it's generally designed for just serving up ROM data, but they built enough connections in that you could also, like it receives interrupts, it receives other things, and yeah, the ARM will usually talk over that thing to the Z80. So the way most of the protection ARMs work is they either have a single external shared RAM that's shared between the Z80 and the ARM, or they have like some kind of banked RAM setup. It's still kind of one of the hardware aspects of this that I need to dig into more. Like a lot of the protection stuff and the ARM stuff I've built in the core right now is just based off what MAME does and some guesses around like how in practice would this operate on the real hardware. Like for instance, the 68000 has this signal called DTAC. I don't know what the pronunciation is. And that's basically a way for hardware to tell the CPU that, hey, you need to wait because I don't have data ready for you. And the IGS-23, the graphics processor, it uses that. If you try to read or write from VRAM while it's reading or writing from VRAM, it will basically tell the CPU like, hey, wait, using that DTAC signal. So that's a way you can like share hardware or share the bus on a Z80 is by using that DTAC signal. That DTAC signal is not on the cartridge bus. So the ARM CPUs don't have a way to tell the 68000 to like, wait while I write to this memory or wait while you access this thing. So I can use that to like at least make assumptions about if you were sharing memory between two CPUs and you don't have that signal available, it means you have to either rely on just racing or maybe the ARM has to wait or some other things. Like kind of until I've had time to like actually analyze that hardware, like making some assumptions around how those things work and at least getting to the point where the games run in protection is where we're at right now. But there might be some aspects that aren't running at correct hardware speed in those cases. There might be some bugs still in how that memory is shared. even though I feel like most of the main motherboard I understand at this point, the variety of probably like 5 or 6 different configurations of protection hardware is still there's still a decent amount of work there.
Yeah, and that's the reason why some games don't run, right?
Yeah, there's a handful of games still that don't run. I think some of them are implemented in MAME and some aren't.
Oh,
There's a confusing array of games and variants on this hardware like I've never seen before. Like some games have like Kitsui probably has like 12 different variations that are
mm-hmm.
supported by MAME, and then if you go talk to the enthusiasts, there's another like 15 or 20 different variations of ROM hacks that they've built for these games too.
Yes.
So just trying to like in my head sometimes like understand what's done and what's left to be done. I get lost sometimes in the amount of different variations and bootlegs and various things that exist.
Yeah, and as a matter of fact, I dumped Ketsui for this the other PCB that's around there, and it's a different variation. But you know, the only difference is that the field is with Fs instead of zeros. So there are some variations that do nothing in
Yeah.
terms of what changed, right? It was just what they had in RAM at the moment of and I mean it's just one example, but there's also the Stoic version that Trap made, and all those hacks that do run on real hardware, and also the Matsuri versions, and you have a bunch of stuff, right? And talking about that, have you played these games? Do you like these games?
So much like with the like going back like on the IRAM stuff, like I'd played R-Type, I'd played some other games. I was familiar with games on that hardware, in the Hunt, stuff like that.
Hmm.
F2, I was like pretty clueless about most of the games
Hmm.
on that system. Like the only one I'd actually really had much experience with was Drift Out, simply because I'm a huge like Neo Drift Out fan on the
That's
Neo
awesome.
Geo.
Yeah.
So like playing the original version was super cool, and like discovering games like Camel Tree and stuff like that was just like, it's one of the things I love about building cores. Like I get an opportunity
Hmm.
to actually sit down and play a bunch of these games when I find it hard to make time to play them in real life. And with the PGM, like I was familiar with, I played like Demon Front. I was familiar with that.
Hmm.
I was not super familiar with any of the cave shooters, and like I just like the look, even though I'm not that great at it. I think terrible is the right word for it. Like the look and the feel of Kitsui is
Hmm.
just like I just love the way that game looks. And I'm kind of sad. I've been watching like Cave like retrospective videos, and I guess it was their last kind of like military
Hmm.
shooter type game, and they moved into more kind of anime character shooters.
Yeah.
But I just like it just looks so cool to me, and it's just like I was amazed when I first built it and I didn't have the sprite scaling in place, and I was like, man, some of these like sprites on screen are a little bit big. I imagine they scale them down when in the real hardware when the sprite scaling is working. And then I fixed the sprite scaling. It's like, no, they actually make these things bigger and they take up more space on screen, and it's even more chaotic than it was when I first looked at it. So um, I'm really taken with that game right now. I just kind of I love playing it. I actually play it on my I have an OLED over here that I have rotated, so I like playing it on that in the dark room. It's strangely relaxing, like for a
It
game that's
is.
so punishing. Just with the music and the patterns, I just like to play it at night to kind of unwind.
Oh yes, I've been well, a bullet hell and shoot 'em up fan for, I don't know, maybe 18 years now. I don't know, and I discovered those games due to this platform, so I have some special love for it. I played the Escaluda port for PS2, and that completely changed me because I was into upscalers. And
Mhm.
obviously, the community that played these games was the community that used upscalers because they cared about input lag and display lag and precision. And there's a lot to unpack there. Talking about precision, how do you feel? Have you received any feedback on the precision? Because people in this community are very particular in how these things play, right?
They are very particular. I've gotten generally good feedback on the core so far. I think there's still Um, there's a little bit of inaccuracy in how the video RAM timing is done, which I don't know. I think it's making the core a little bit slower than it should be. Like if you run both games, like if you run some real hardware and the game side by side, I think after a few minutes the core will be behind by like a second or so, and that's something I need to just dig into, and like how the actual, like what is the precise um, kind of scheduling between background RAM reads and CPU RAM access.
I see.
I think that's the last kind of like timing inaccuracy there. There's still some back and forth over like whether the tempo of the music is exactly right. It was super off on the first core release because the way the sound processor was generating interrupts was not accurate. That's should be fixed right now. But a few people have said they feel the tempo is still a little bit off, so I need to dig into that too. Like the sound CPU, the sound processor has been this kind of like really interesting journey, because when I started off, I was like, I've never built a sound processor before. I've always kind of had the luxury of having someone else has built it in the past. And I knew the MAME implementation was not super accurate. I even found out that it took a while to discover this, but like MAME actually thinks that all the audio or most of the audio being played back is 16-bit. But this platform actually doesn't support 16-bit. The CPU, the sound processor supports 16-bit audio, but the PGM cannot. The way the ROM is mapped, it can't actually play back 16-bit. So MAME could sound super crunchy in certain areas. And just how the volume ramps and a bunch of other stuff work on there has been an interesting thing to discover. Like so the way I developed it was I took the MAME source code and I ported that to Verilog, and like knew that was not going to be accurate, but it was a good starting point. And then I built some firmware that I could hook up to the digital output on the chip itself, so I could just capture the raw audio coming out of there before it goes into the DAC and before it goes into the analog circuitry, so I could get like direct digital output from the chip, and then I could start programming it just with like playback a sample, and then like get to a point where the hardware and the core like matched binary to binary for like actual sample playback. So that was kind of the first stage, but then there's a whole bunch of stuff around like when do interrupts trigger, how are those interrupts like handled, when do those flags get cleared, a bunch of stuff like that really comes into kind of the tighter timing of like how the Z80 CPU and the sound processor interact with each other. So I think that's in a pretty good state. I want to port a bunch of that stuff back to MAME, because most of it is not really kind of hardware critical. It's more around things like what are the actual like volume ramp tables, and how does like what's the timing on certain things. But it's it should be pretty easy to get MAME sounding much better than it is right now.
That's awesome. It's a very important part, well, at least for me, that most people don't appreciate that much. But you made this tool called the PGM audio extractor for this, right?
Yeah, I built it's just a like a Pico Pi microcontroller hooked up to like soldered onto the sound chip itself, because it just outputs. It's kind of like I2S. I2S audio. It's similar
awesome.
to that it outputs. So I just had to hook up something to capture that. So yeah, I can get like I'm used, like instead of having to be like, okay, it kind of like the analog outputs are kind of similar, like being able to just see like what are the actual like byte values being output from this thing has been great, because I could do stuff like just there's like internally there's a volume table that converts like the linear kind of volume values you're feeding into like a non-linear multiplier for the output volumes, and I was able to extract what that exact table is by just playing a single like frozen sample at a known value, and then just ramp that up and down across the volumes, and then read what values I was getting out of the chip.
That's amazing. And is that table? Do you think that table is for attenuation when you have several samples playing at once? You don't saturate the signal, probably.
They used, I think the purpose they used it for was that they wanted to be able to have a kind of like just a non-linear volume curve.
Okay.
Um, there's a similar kind of pan table too that has kind of an exponential fall off as you move left or right. Um, but it's interesting because it's a stereo chip, but it all gets munged into a single mono channel
Okay.
on the arcade hardware.
Yeah,
Uh,
yeah.
but I will. The interesting thing about audio is like I have received almost zero feedback on audio um, on any of the cores I've built. Like people have just said like this sounds good. These effects might sound loud or something. Um, on like from the cave shooter fans, like I've received so much feedback on like tempo and exact
Mm.
like volume mismatches. Um, Someone even called out that, like I can't remember what their exact description of the audio was, but like it like there's like a like I showed you like the MD Fourier
Mm-hmm.
output, and like there's a slight like like 6 decibel like difference on the high end and like 3 decibel difference on the low end. And someone's description of how they felt the sound sounded different from arcade hardware, like perfectly matched that curve. And I was like, man, people really, really, really not just like the pixels on screen or the speed of the game, but like the level of focus people have on the audio in these games too is like nothing I've ever experienced on a core before.
That's that's great to hear. And
Yeah.
and now that you mentioned Andy Fourier and the combination of this, first of all, do games support stereo internally, or do have some separation in stereo internally, or it's just all mono from the source code as well?
I think it's all mono. I haven't looked too closely at it, but like I haven't seen any real like I went through and like extracted out the pan tables and kind of expected there to be some difference in the sound of games, but it really wasn't. It really didn't make any difference, and
Mm-hmm.
I think I don't even know if games even make any adjustments to those pan values other than just center them all.
I bet they don't, because that was very common in many games. There's a lot of arcade hardware that did have stereo capabilities, but never used them. They were at the chip level, but not at the PCB level, right? Because in an arcade setup, only Konami was really into making them stereo, and it makes a great difference. But in that scenario, you hardly ever listen to the stereo, right?
Yeah, I think it's kind of a shame. Like I think this sound processor is more capable than most, and I feel it's a little bit underutilized. Like the
Mm.
fact that none of the games can support 16-bit audio um, is unfortunate. The way 16-bit works is you actually have to like split the ROM into two 8-bit ROMs, which
Mm.
is kind of it's a weird hardware limitation on how they've built it. Like you can't really mix 8-bit and 16-bit audio with this chip. You kind of have to decide like everything's going to be 16-bit or everything's going to be 8-bit. Um, and then the power amplifier on the board can operate in a stereo mode as well. Like it can either be a 20-watt stereo amplifier or a 40-watt mono amplifier, and they've configured it as a mono amplifier. But like this is like late 90s. This PGM hardware, I imagine, would be like potentially like permanently installed in an arcade cabinet and you're swapping cartridges. So like it seems like you could have gone down a path of supporting stereo as an option on this board, and it would have been utilized by people at that. I can understand like early 90s games just being mono, but like late 90s, early 2000s, I think it's a shame it doesn't support stereo.
I fully agree. It's a real shame that it doesn't, because it has some pretty good music. I mean, Donlon, Yo, Speruda, Ketsui, they all have amazing music, right?
Yeah, I've kind of been wondering too if like if some of the modern ports have like higher fidelity 16-bit
Yes,
audio or higher sample rates, and if it would be possible at all to kind of like backport those onto the original ROMs.
that'll be amazing. Yeah, but I do know that some of these games do. There's also CD versions of some soundtracks, so that also works. But the M2 ports for the PlayStation 4, they do have some higher quality and some arranged versions as well.
Yeah.
And well, now that you mentioned MD Fourier, how hard was it to port MD Fourier to this system?
It was. I've done it like 4 times now. This one was easier because it really just is like there's no, there's no noise channel. There's no like FM synthesis. It's just sample playback. So it was kind of just find a sample that's like a cleanish tone, and then play that back at various frequencies, and that's really what I had to do. I think the problems I had were I think the usual problems I run into is just not properly generating a sync signal, and things like that.
Yeah, I remember that.
Yeah, I feel like every year or so I reach out to you and like, please help me work out why this is not being.
And you already had it done, like completely. Like usually when this happens, I am the one that does the profile and does all the things. So it's awesome that just come in and it's already done, and it's just some very minuscule thing that's in your way usually.
I think the surprise for me was usually, and I haven't worked out like how to like. There's I guess 2 questions I have is like there's after the DAC there's a quad op amp, and it does some kind of filtering, and usually that filtering on arcade hardware is some kind of low pass filter.
Yeah, typically, yeah, it is. Yes,
it gets rid of like all of the awful high frequencies that are coming out of like their like cheap PCM hardware playback systems and things like that. Here, that doesn't seem to be the case. It seems to actually be boosting higher frequencies and kind of like and attenuating bass a little bit.
So it's doing what we saw in the curve, or it's just making it flatter.
It seems like it's doing what we saw in that curve. And then the other question I have is I'm wondering do these cave boards have the same filters on them, or have they changed the filters on the boards? So I'm going to actually have to trace out the motherboard and understand all the different the RC networks going into the op amp, so I can do some analysis on what the actual filters are doing. But it's not what I expected it to be, and I was kind of hoping it would have a bunch of, because some of the games. Not the cave ones, but some of the other ones, like they do have kind of like a sharp tenor to them. Sometimes it's a little bit difficult on the ears. So I was kind of hoping that the hardware had a more aggressive low pass filter on there to kind of smooth that out, but it does not.
It does not. The cardboard, right?
Yeah.
It does not, because it's this is the original version of the system, and these were made for the cave releases, and I believe Demon Front is also available in this format, right? Yeah. I don't have that version, but now that we're focusing on audio, we'll move into some other territory in a minute. But this says wavefront. Is this? I know that probably the answer is yes. Is this very similar to how a wavetable sound card in PCs worked?
Yes. So it was. Someone pointed out to me. I won't mention the name because they don't want to be mentioned, but they know who they are. That like this chip is very similar to the chip used in the Gravis Ultrasound PC sound card, and that there was like a decap project done on that recently. So like there's Verilog implementation of that's based off of that decap. So that was useful, just kind of understanding like building a chip like this, how would you do certain things?
Oh, that's awesome.
Under the assumption that like this is probably not a completely unique design from this company. They're probably all from a similar family of how these things operate. And a lot of the registers that this chip has are the same as the ultrasound registers are. So there was that use case. This chip itself is also used on some Turtle Beach sound card, like PC sound cards. And those sound cards are still supported in Linux. So I could actually look at the Linux drivers and see what kind of information they were writing to the chip. And that's where I was able to work out like that it was actually like how the 16-bit and 8-bit like modes are set up, and a bunch of stuff around how the volume things are set up and how the interrupts are handled. Even more useful is like that sound card, that Turtle Beach sound card. It has the the PC doesn't talk directly to this chip. It talks to a Z80 on that chip that then talks to this sound chip. And someone pointed me at the BIOS for that sound card that I was able to reverse engineer and pull a bunch of additional information out of that. So having the Linux drivers, the reverse engineered BIOS, was able to answer a whole bunch of questions about how various parts of this chip operated. So pulling all those sources together, I was able to. I think I'm at a pretty good approximation of what this chip does, and I got much further than I thought I would be able to get with this. Like, this was kind of something, when I started on this system, I put this in the back of my mind, I know, based on my experience, I've got high confidence that I can deal with the CPU, I can deal with the graphics processor, I can eventually deal with the protection systems. Like, those are all just kind of like things I understood as like, I know how to do these things, it's just going to take time to get to them. The sound stuff was like, I really have no idea where I'm going to start with this. And gradually finding all these sources of data on this thing and additional sources of information kind of made it more and more achievable in my mind as I got closer and closer to having to work on it.
And now with that experience in your mind, do you feel that it's less difficult, more difficult, the same thing as the other areas that you just mentioned, like security, CPU, data communication?
I think this might be a little bit easier. I think the fact that, again, it's a more modern sound chip. It's just doing wavetable,
not
playback,
synthesis,
not doing any kind of synthesis or sound stuff. So I'm not like dealing with like this kind of like, potentially maybe analogish type stuff. It's all just pure digital. And I think the fact that audio is just kind of a linear like time series output makes it really easy to analyze, like, change a value and look what the output is and compare that against two different outputs. It's much more difficult in like a graphics processor where you're outputting an entire frame of information. There's a lot of different variables that can change. It just like sound just seems a little bit simpler in that regard, especially in the purely digital domain.
Yeah, I completely follow and understand why you mentioned that. Now you mentioned the video part of the system, right? This is the card based PCB, and what are this that are on top here? We have the sound. All of this is just the sound, right? And here is a connector. Here's the deadly battery that has killed a bunch of PCBs, cave PCBs, and also PGMs, right? Because this battery just exploded or just corroded everything around it. And unfortunately, there's some signals here that have the DTEC and also have the bus signals for the 68,000 that come all the way from this ROM to the CPU, exactly where this happens, right? And same thing here in this one. It's usually below this this port that has. I had the pleasure to document this, but it's a port for 4-player and audio and video as well. It sends it from here, right? And it switches. So the battery usually makes the PCB stop working when it leaks.
Yeah, it's a really interesting design in that, like, they're like all that RAM next to the Z80 or next to the dip switch, I guess, up in the top right hand side. Like that's the system, that's the CPU RAM, and it's actually this like low power RAM that can operate at 5 volts or 3.3 volts because the entire RAM is kept alive by the battery when the system's turned off.
Oh,
like it's not just like they have a single like NVRAM chip somewhere that stores like things. It's like that all those 4 RAM chips are kept clocked during power down by that battery. So when that battery dies and it starts corroding through those traces, like it's super easy for those traces to start interfering with the bus and other things because it's so interconnected.
I see.
But yeah, like there's some like that's like kind of one of these interesting choices where like you can kind of tell that like, hey, RAM was a lot cheaper now than it was 10 years before, when they can just put all of this battery back RAM on there and choose to pick probably what was a more expensive RAM chip that could be battery backed up.
I see. I always thought this had something to do with the BIOS backup, And you have the 68,000. And what are those chips that they are scratched in the cave PCB, but not here?
Yeah, those are the IGS 26, I think.
Mm-hmm.
And they seem to just be like it's weird that right between them is like that PAL chip.
Mm-hmm.
Um, because those two chips just seem to be um, like very specific ASICs that they've built that generally just do input and output, and they're both the same chips. They're both IGS 26s, but they do very different things. So I think there's probably a mode select pin on them that changes what they do, because the one closest to the edge connector, that is that one generally just deals with all of the input and output for the controllers, for the player inputs, and the kind of like coin events and start buttons and the coin counter outputs. Meanwhile, the one over closer to the Z80, like it controls all access to RAM. Like basically every signal on the Z80 goes through that thing. Like the Z80 is completely isolated from the RAM and from the ICS 2115 sound chip. It all goes through that IGS 26 chip next to there, and it manages. It gives the Z80 access, or not the Z80. It gives the 68,000 access to audio RAM, because there's no ROM for the Z80. It writes the 68,000 writes into the Z80 RAM, and everything runs out of the Z80 RAM. And it manages interrupts, it manages a bunch of other things. So there are two chips. They're the exact same chip. They do very, very different things.
That's
So it's funny that they built these two chips to solve all of this kind of interconnects between these things, and then either they forgot a few things or discovered a few things, and they had to put that PAL on there to fix a few other issues. Like that PAL does some it does some management for the timer and the clock battery over there. It does it does a small bit of the interrupt processing for the Z80 and the sound chip. So it's kind of like these things where after they built those two ASICs, they were like, oh God, we need one more signal here. So we've got to put a PAL on the board and solve a few of those problems.
that's really interesting. So basically, they recycled it, reused it, and adapted to manage everything.
Yeah.
And this chip here,
That might be the music ROM, is it?
yes, it is. I
Yeah.
believe so. Yeah. So this music ROM it's not in the cartridge, right? It's just for the C80 in the main PCB.
Yeah, it contains music data, and it contains a mix of there's a bunch of like wavetable samples on there that ICS made, and it's part of their kind of official kind of
Soundboard, right?
like soundboard that they sell with these chips. So it contains a bunch of information. I don't believe the games use any of that stuff, and
They
then
could.
there's also a bunch of like PGM specific stuff added onto it as well. So it's kind of a mix. Like on the Turtle Beach sound card I looked at, it has the same ROM chip on there
I
in
see.
the first half, and then the second half is all PGM specific stuff.
That's really interesting. And it's never used, right? They could have, but they didn't.
Yeah, there's a way on the sound processor that you can just use it to read ROM memory back to the Z80. And the sound card uses that to read all of that kind of metadata out of there, so it understands like, hey, here's all these different like MIDI patch tables and stuff like that for doing MIDI emulation, and that's all on there. So like there is like a full kind of like MIDI soundscape on there that you could use to do a bunch of stuff, but no game seemed to use it.
That's amazing. Yeah, it's kind of a remnant of its history as being part of the PC. And I bet they could have thought about using just MIDI for this, right?
Yeah, yeah.
And now this chip.
This is the IGS 23. So it's the main video chip. It's the only video chip. It's actually really nice and clean. coming from the F2 was kind of like, I don't know what they were doing. Like they were like some of the chips on the F2 were like pretty old, like late 80s, and kind of super early, kind of like Sprite, like thoughts on how like Sprite hardware should work, I think. And they were super finicky. They were like really difficult to work with. It was like frame buffered and double buffered Sprite data, so things
Mm.
were kind of like 3 frames behind in some cases, and a really complicated way of like managing CPU access to these things. This, on the other, and contrasting it to like IRAM stuff, which was always kind of like very scrappy, I would say. Like the IRAM
Mm.
stuff was like, what can we do with as little hardware as possible, to get some really good results? This is kind of like luxurious, I would say, in that like it is, you got all those sprites. They can be super huge. You have this big chunky like 32 by 32 scrolling tile there in the background. Everything is super clean. There is so much wasted memory here. Like the palette RAM takes like two, I think they're either 8K or 16K chips. So like there's 3 RAM chips connected to this. There's like a VRAM one, and then there's a palette RAM, and the palette RAM I think is like 32K of memory, but really only 8K of is ever used. Um, the VRAM has a bunch of unused space in it. Like I kept kind of expecting to find hidden functionality, because IRAM especially would just hide random, like, oh, if you want to like double buffer or triple buffer the palette RAM, sure, we got a few bits left over. Let's allow you to swap these pins around and do different things. It's very simple. It's almost boring in how it's implemented. Um, there's some interesting stuff in like um, the tiles are like, they're like 20 bytes of memory for the tiles, which means like there's not a, usually you're used to these things being like powers of 2, because it makes it really easy in
Mm-hmm.
hardware to calculate addresses. So like you have to do a divide by 20 at a certain point, to actually calculate an address in ROM to read from, which is a very strange thing to do, and just kind of points to like, I've heard people say like, IGM, or IGS had like a lot of money to build this system, and I keep kind of finding evidence of things being just kind of like over engineered and just having a lot of resources to throw at this problem.
Interesting. So you have these ramps that you mentioned, and this chip here.
That is the tile, ROM for the BIOS. So the BIOS comes with like, there's a program ROM, there's tile ROM, and there's music ROM, which is kind of nice, because I knew when I started working on it, like the BIOS has like all of the information I need to like exercise a bunch of systems here. Like the only thing the BIOS doesn't have is any Sprite data.
Hmm.
But I could get a whole bunch of stuff running, and I could build tests, because I had all of this tile data and music data in the BIOS that I could use for stuff. So like it contains the like the boot up animation, and fonts that a lot of games use for basic text rendering, and music and coin insert things and stuff like that.
That's really interesting as well. And regarding the precision or the how about fidelity regarding this and video, what can you tell us?
So it's a strange resolution. It's 448 by 224.
Mm-hmm.
So it's like, it's 224p, but it's like it's non-square pixels. Like the pixels are almost, like twice as wide as they are tall. So it does have like really nice high resolution on its horizontal axis. But if you look at things like actual like square pixel size, everything looks stretched and fat. So but it does, like, it's like it's 5-bit color for the tile maps and the sprites. There's 60-bit color for the text overlay. It supports, I think, like 32 palettes for each. So like the tile maps
Mm-hmm.
and the sprites have 32 colors each. I think it's kind of a miss that the sprites don't support more colors in an individual sprite, but it's still, they still look. There's
Yeah.
some amazing sprite artwork on this thing. The F2 has 16, like 64 color sprites that are only used in Final Blow, and I think none of those games ever looked super visually impressive to me, and it's less about the hardware and more about just, I think, the style that they chose for a lot of their games. Um, I think games like the Cave Shooters and Demon Front and the Gladiator have just such beautiful sprite work on this system. It looks amazing.
Oh yes, they made some impressive stuff post Neo Geo, and they were alive while the arcade was dead, or at least
Mhm.
dying in some senses, and you only had the Naomi, right? And the
Yeah.
specific PlayStation and GameCube based platforms. So this is kind of that original line that's still JAMA and still that 15 kilohertz, right?
Yeah, still 15 kilohertz. It's and I think just having like the huge ROMs they have on these things for the sprites, like the sprites are, they clearly spent some time thinking about how to best compress sprite data, because the way it's stored, someone said it's kind of like some of the later Sega systems. It's not just like, a lot of arcade hardware, the sprites are kind of very similar to how the tiles are stored, where it's just kind of like a grid of color data. On this, you have two sprite ROMs. One is the B ROM, which is just a bit mask of which pixels are transparent and which ones are not. And then the color data is just a kind of like a stream of, it's called the A ROM. It's just a stream of color values. So all like transparent pixels aren't represented in the color data at all, which means the sprites are this very kind of strange format, and there's some hoops the hardware has to jump through. If a sprite is kind of like off screen, like off the top of the screen,
Yeah.
it needs to, in the vertical blank, it needs to like scan through all that sprite data to find what's the first pixel visible on screen, because there's no direct mapping from like going from like a position within a sprite to an actual color value. You have to iterate through the entire sprite to that point in time, to actually know what color value to use.
So basically, you're wasting those cycles, right?
Yeah. But it means that the sprites can be like, the sprite data itself is pretty compressed, because any like transparent pixel values just aren't in the sprite data at all. While in a lot of other systems, you'd have to have that full kind of like, you'd have to have all those pixels even if they weren't visible on screen.
I see. Now, there's a question that one of my friends have regarding these. I don't know if you can see this specific. Let me just zoom it in. Here is an
Oh,
example of
the
how,
corruption here.
yeah, the corruption, and why would that happen in real hardware?
So I will say, first of all, like when I saw this happening the first time, like someone showed me this video, I was like, I'm pretty sure I'm never going to do this on the core, because this is actually kind of what I was just talking about, in that like as the hardware is running line by line,
Mm-hmm.
like it's not drawing the sprites to a frame buffer. It's like each line it's drawing on screen, it's going, okay, what on this line, on this horizontal line on screen, what sprites are visible, and it's iterating through all of the sprites, all 256 sprites, to find out which ones are visible at this point on screen, and drawing their colors out. And it has to keep track of like where it is in each sprite, because as I said, like that color data for the sprite is like, it's just a linear list of color values. And if a pixel is transparent, it doesn't draw any value out of that list. It's only drawing stuff out of that list of values if it's an opaque pixel on screen. If it runs out of time as it's trying to draw those sprites, then that kind of like color pointer doesn't get updated correctly. And then you start having these values, like you just kind of get these random color values on here, because it's running out of time to draw the sprites on screen. So um, if you have more than 80 sprites per line, that's the maximum it can actually get through. It will start running out of time to process those sprites, and then the color data gets out of sync, and things kind of start looking like this. Um, on the FPGA, there's like a lot of buffering and stuff that needs to be done to deal with like latency of SDRAM, SDR RAM memory, and DDR memory. So I'm always kind of like trying to keep ahead of where the hardware would be on its sprite rendering, and trying to get to the point where this would accurately be reproduced. I think there's a lot of different kind of counters and steps in the hardware that you'd have to understand to really get this to this point. But maybe someday if we had an FPGA with a ton of memory on it.
Yeah, because you're dealing with external memory that you're just managing yourself, right?
Yeah, yeah. Like we have to like the on the real hardware, it can read a ROM in like 20 nanoseconds or something like that, and a value from that, and we don't have that. SDRAM can't run that fast.
Yeah, and they say in the chat that so the FPGA, the MiSTer FPGA, is optimized not to have this box.
Let's think of it that way.
Yeah, of course.
I know, like it would be a really great sign of accuracy, like like this doesn't affect kind of like the speed
Yes,
of
yes, yes,
gameplay.
yes.
It's really just visually, like really the only thing that actually affects the speed is like how fast the CPU is running, which we're pretty confident in the accuracy of that because of the FX 68K implementation we're using. And then the other thing is just how access to video RAM is managed, because that's the major slowdown on the CPU. Is like when can it access video RAM, and how is that access gated? Like that's the kind of thing that slows down the system. That's something that's hard for MAME to replicate because it requires kind of like cycle level
Mm-hmm.
accuracy on these accesses. But once right at the start of the vertical blank, I think one line before the vertical blank, the um, the IGS-23, the video processor, it basically stalls out the CPU and it copies a bunch of data from RAM. It accesses the CPU RAM directly and copies all the sprite data into its internal memory, and then that's what it draws from for the next frame. So kind of that's that part right there, that like copy, that DMA of memory from CPU memory into its internal memory. Like that's the only interaction between the CPU and the IGS-23 as far as sprite rendering is concerned.
See, so with this is the sprite rendering. Now on this PCV, I was just looking at it, and you mentioned this IC26 that this one manages the C80, this one manages the inputs. This is the 68,000. Now I'm guessing this is the IC23, and what is this that's just next to the BIOS then?
What is that? This is a cave.
Yeah, this is Escaruda, as a matter of fact.
I don't know. Does it might have ARM protection on there, so maybe
Yeah,
that's it. I can't see it on your. Is it? I assume it's all.
yeah, it's just scratched out. I'm guessing it's the ARM CPU, and
Yeah,
this one is the IC23 because they do
yeah,
look kind of similar, right? This is the cart, and this
mhm,
is the ARM, right? That's in
yeah,
the
yeah,
cart, so it kind of looks like the same kind of thing, right?
yeah.
And I wanted to ask you about this cards. This is the one that we dumped back in the day with David Haywood. For just what they told me is that we didn't have access to the internal ROM code, right? So
Mhm.
we had to just place a different BIOS in here that had doubled the the memory, and we placed a switch, so we just flipped it and changed the complete address space for the ARM when it was already boot up, and we could just run from the ARM and make it dump everything to the screen, right? That's how it worked back then. But that internal ROM, my question was, what does it do? This is how it was done. Here is the photo of when we dumped that back in the day. David Haywood did all the hacking. I just was blind hands, his remote hands, and in doing that. Right here is a screenshot of how this was dumped. So we basically just took screenshots of the whole thing, and this was just converted into the internal ROM, and this is how this was done back in the day, about 16 years ago.
I had no idea. This is fascinating. I didn't know you were involved in this.
I was just tangentially involved in this because I was part. Well, I'm still part of the dumping union, and just I don't have as much hardware or getting hardware as back in the day, and it was an amazing experience. And David Haywood just walked me through what we needed to do to to dump this internal ROMs, right? Because the Gladiator was one of those ROMs that we didn't have
Hmm.
for internally in the system, and this was just a card. As you can see, we placed that different ROM here in the cart. We changed this, and we had that PDT switch, and we just flipped it to change the address space after it was put up, and we could dump the things. With the dip switches, we could change the addresses. So the dip switches were used as an input to change the address space and just take photos of everything, and they could just transcribe it. I believe they had some that the ROM was colored, so they could just use the recognition software to
Hmm.
check everything, right? And the question was, what is this ROM in the cart used for? Because this is very elaborate for just a cart, right?
Yeah. So like in this case, what game is this?
This is the Gladiator.
Okay. So Gladiator, I'm not sure what it uses ROM for. There's a variation from like some games just use it for protection.
Yeah.
Like just use the ARM CPU for protection. Like some of the cave shooters, they they do some stuff where like the actual like sprite positions on screen are calculated by the ARM CPU. Um, and it's like the Z80 gives it some information, and then it writes back like draw the sprite at this position. And I had some values messed up, and I thought I was just in like an extremely difficult version of Ketsui where all the enemies attack from the bottom of the screen, but it turns out the protection was incorrect, and it was returning the wrong values. Um, but then games like SVG and Demon Front,
Mm-hmm.
like they'd run a large amount of their gameplay logic on the ARM CPUs, and the Z80 is generally just there to kind of like push stuff to the screen. So it's like the purposes changed over time. Like the earlier games of like very limited ARM CPUs with just a tiny amount of RAM and some internal ROM, and they're mainly just for protection. And then later games use them to actually run a bunch of the code, because they're 24 megahertz ARM7 CPUs compared to like a 12 megahertz Z80, so they can do a lot more.
The 68,000, right?
Yeah,
Yeah.
yeah, 68,000. But the dumping stuff is fascinating. Like I'm kind of like there's still a bunch of undumped games. There's games where like the external ARM ROMs have been dumped, but there's like a small internal ROM that has
Mm-hmm.
not been dumped, and like MAME contains like people have built kind of alternative internal ROMs
Okay.
to boot them up. Um, I don't know if you know James from Retro HQ, but he's working on
Yeah.
a flash card for PGM,
Yeah.
and he to support to avoid having to like build a bunch of simulation stuff like MAME does in his flash card. He took the MAME simulations and rewrote them as ARM code, and published those on his GitHub. And then like that's what I use for some of the games that don't have their internal ROMs used. I use his alternative ARM versions of the MAME simulation on the core to load these games. So like there's some stuff like there's a lot of things that have happened recently with like ARM like voltage glitching and other things to expose
Mm.
internal ROMs, and I'm wondering if any of that would be applicable to this hardware at some point. But it's kind of I don't know if it's something I would ever get into, but it does seem like an interesting direction.
If you have a list of the ones that are missing, and I do have some, I could replicate that. I still have the code that we used here,
Yeah.
so that I could send you that if that is useful in
Yeah.
any way.
The one thing I'm very interested about these carts is like you'll see this. I think there's two RAM chips up in the top left hand corner that are surrounded by a bunch of like buffers, or maybe like 74 series like multiplexers or something. I think this is the banked memory that's shared between the ARM CPU and the 68,000. And then there's like one CPU is accessing one of these while the other CPU is accessing the other one, and then
Okay.
I believe the
And they
ARM can
swapped them.
switch which one is kind of like is being used by which at each point in time. So there's a few different variations on the different cartridges of how the ARM and the 68,000 talk to each other. This, I think, is kind of the final iteration, which has the most memory and the most kind of like flexibility for how they talk.
Yeah, this is the Gladiator, so it's a pretty late title, right?
Yeah.
It's
Yeah, and
very
like you
impressive.
look at how complicated that card is, and you're like, man, if they could have just if they built this system maybe around an ARM 7 instead of around the 68,000, like what else could it have done if it had those kind of capabilities?
Yeah, that would be impressive because there's very little arcade games that do have an ARM CPU as the main one. I believe Strider's second part, like Osman, does they
Hmm.
have one, right? But it's very uncommon
Yeah,
for ARM to be the main CPU. It was, as you mentioned earlier, dominated by 68,000.
yeah. I mean, like this board has probably more processing power. This like cartridge board probably has more processing power than most arcade systems from the 80s, I would say.
Yeah,
This is
and it's just a cart, right?
it's just half a cart. There's still
Yeah, yeah,
the
yeah. The
yeah,
other half is the one that has the ROMs, right?
yeah, yeah,
This is just operations. This is computing power, basically.
yeah, yeah.
And this protection, you mentioned that it's sometimes it calculates stuff, and that was very common as well in the 80s with MCUs, right? Bubble was one of the famous examples, and you also had the Gaelco PCBs that have an MCU, and Data East had MCUs for protection, and that was kind of the way that games were protected from piracy, from bootlegs, right?
Hmm.
And
Yeah,
are you
yeah.
aware of bootlegs here? Yeah, sorry.
Some of the like the other Taito games like Kadash, I think, and some
Mm.
other ones have like there's the C chip. I think it's used in like Operation Wolf and some other games too, as one of their main protection systems.
Are there any bootleg games from the era that you know about on PGM?
Um, there's a few like the cave shooters all have bootlegs. I don't know of anything that's kind of off the beaten path. The only one I'm kind of like IQ 132, who did a bunch of early PGM research. Like he was in the middle of porting Cabal to PGM, and someone actually built an MRA for the core that actually like can run that game. It doesn't have any audio, but it seems like a semi-working version of that game ported to this hardware.
Wow, that's that's impressive. I didn't know about that port.
Yeah, I've toyed with the idea of like maybe building some kind of development kit like that would allow people to do some porting, because it would be interesting to port some, see how difficult it would be to port like a Neo Geo, like actually port something like Metal Slug
Mm.
to the PGM would be kind of an interesting project.
Yeah, I bet that'll be really interesting. And talking about that and protection, some of the games are encrypted.
Yes, yeah. There's a few different ways that's done. There is like some of the earlier games have a dedicated. They don't have an ARM CPU. They've got a dedicated like chip that does encryption. And then there's a on a lot of these ARM games there is a they have like an XOR table that they write bytes into, and then that's used to decrypt ROMs as they're being read. So it's kind of like there's a few different ways that they do encryption, and sometimes it's just dedicated hardware that does the encryption.
I see.
It's not super complicated. It is tedious code. I'm super. This is one area where I'm like, I'm so glad MAME exists, because if I had to sit down and work out what these different encryption tables are, I would have not done this project.
Yeah.
Basically,
No, yeah, I fully understand. MAME is impressive. It's a great source of. I usually, before entering the arcade collector area and some development, I used to think of MAME just as an emulator, right? And it's so more richer when you see the source code.
I mean, the source code, the debuggers that are
Oh
built in, like
yes,
a whole bunch of stuff. The ability to like to build scripts and generate traces, like it's so useful in so many ways that I think people often simplify it down to like, oh, is this a main port or not? And like everything in my mind starts with main, because it's just such a source of not just a source of information, but such a useful tool for
oh
development.
yes. Yes, it's impressive when you start just like poking around and start using MAME to debug. It's amazing how well it behaves. Right? It's so stable and so easy. Well, not necessarily easy to use, but so convenient.
Yes. Yeah, like when people will often ask me like, is such a core possible on MiSTer, or like how complex would a thing be? Like the first thing I do when someone asks me a question like that is I go look at what's the MAME implementation look like, because from there you can quickly understand like what kind of sprite system does it have, what kind of
Mm.
tile maps does it have, how much memory is it expected to access, all those kind of things.
Yeah, when I was developing for the Sega CD, it was the only way to debug.
Yeah.
Yeah. And now that we talked about how this works, how different is the PGM2? Have you taken a look into that?
The PGM2,
Yeah.
I don't know. I haven't. I've kind of put it out of my mind. Again, I need like things near on the horizon so I don't
Mm-hmm.
get discouraged
Yeah,
from doing.
overwhelmed as well.
Yeah, I think the PGM2, I believe it has a more powerful version of the graphics processor. I think it has a 6820 CPU. And beyond that, I don't actually know. And then there's the PGM3, which I think is almost completely different.
Yes. Yeah. That's a completely different beast, and there were different ports for these things. I saw that there was this tweet by Shane that said that as a software developer guy, I find myself when reverse engineering hardware or develop an FPGA course, I always need to write custom ROMs to understand the hardware from a software perspective, right?
Mhm.
And I obviously empathize with this. What tools did you build for this?
So I built this so we've talked about this one before, but like I
Yeah.
built years ago, I built like these like Pico ROM
Oh, they are
chips
amazing. Yeah.
for just so I could like quickly like run code on arcade hardware. Like that was my main motivation for building those. And I used those for years. And then when I looked at the PGM, it was like, okay, it uses larger ROM chips.
Mm-hmm.
It doesn't like, there's nothing I can easily slot in. And I thought about it a while for like maybe desoldering the BIOS chip and putting my own BIOS chip in there. But then I built this one for
Mm-hmm.
which uses the same, like pretty much the same software that these use, but it's configured for the PGM, and it just replaces the program ROM, basically replaces the BIOS ROM, and then that allowed me to like very quickly develop software. Like I don't know how many. I'd have to look in my GitHub to see just how many different test ROMs I've built at this point, but like it's
Link is in
in
the
the
chat.
huh.
I tell people link is in the chat because I just
Okay,
placed
yeah.
that link for your test ROMs in the chat.
Yeah, so like in the core directory, there's like a test ROMs folder, and like the way I approach this is like I try to build a little library that will let me get stuff on screen, so I can like at least print text and show stuff on there, um, and then I kind of build on top of that. So there's a whole bunch of ROMs in there for like testing audio things. There's a bunch in there for just kind of like draw a sprite on screen and make it smaller and bigger and allow you to adjust that. And the other thing I do too, one thing that changed with when I started building the F2 core was I leaned more on using uh, a simulator on so like I
Mm.
can run the core on my laptop in a simulator, um, and I built a GUI for that displays the video output. You can send input, you can load ROMs. Um, so that's like the process is often like build a test ROM, get it working on MAME where it will run at full speed, then get it working in my simulator where it runs at about like 2 frames per second, and then run it on like real hardware, and then run it on my core on the MiSTer FPGA. So having all those four places to run these things and compare results. Um, I think the other kind of big change in my development process is adding safe state support,
Oh.
um, which is super useful, especially when like you consider like the simulator runs at like now with all of the protection stuff on the ARM CPUs, it runs at about like a frame per second. Um, so I'll often do stuff like go run something on the MiSTer FPGA itself, get to a point where like something's broken, like a sprite's not rendering correctly on screen, capture a save state, and then go load that save state up in the simulator, where I can then just like easily analyze every single aspect or make changes to the code and see how that affects the affects the save state. And plus, if people have bugs they're encountering, they can just send me those save state files, and I can
Wow.
reproduce those bugs recently. And it's really like, I kind of thought save states for development weren't that big a deal, and then it was really Robert Pipe working on all his cores and seeing how quickly he could iterate on PlayStation and stuff like that. I was like, oh, this is actually a huge deal. And now I can't really imagine, like, when I have to actually like iterate on a problem on the MiSTer FPGA and deal with like 20 to 30-minute build times, and then running it and it's still broken, and then going back, making a change and running again. It's like, I try to avoid that cycle
Completely. Yeah.
as much as possible now. And plus having it in a simulator, I can just work on my laptop downstairs and do most of my work that way, and then come up here and test it out on real hardware or build a core and do it there. So I optimize my workflow around being on the couch as much as possible.
That's really amazing. And yes, now that you mentioned how it works, I can't imagine working without that. It's like having a core dump from the user when something goes wrong, almost, right? Because it's
Yeah,
after,
like,
it's before the fact, not after.
yeah, like it can be like sometimes either or. Like some people will send me dumps of like, hey, if you load up the save state, then like a minute later something will be broken, and that's great too, because sometimes I don't really want to know or it's not super useful sometimes knowing what the broken state is. It's more like, how did it get to the broken state?
Yes, of course.
But just having that, like in the simulator, you can look at every single value for every single signal inside the core,
Wow.
which is like super useful, versus on real FPGA hardware, you have to like select, this is the particular signal I want to be able to see, and I can see like maybe a millisecond of that value. But with the simulator, you just have such visibility into what's going on.
Yeah, that's impressive. And how hard was it to implement the save states? Because I've heard that for a complete core, it's a pain, right? But I'm guessing that it changed completely doing it from the ground up.
Yeah, like I did it pretty early on the F2 core, and it was, some things were pretty tricky. Like you said, like if you build stuff with it in mind, you kind of think about it from day one. You're like, okay, I'm building this sound processor and it has all these register values, so I need to make sure, how do these registers get read by the sound processor, and also how do they get saved out as part of save states? And you kind of just, you build your stuff with that in mind. For the F2, I was dealing with like I had Hotego's like Yamaha sound implementation, so I had to build a script that would kind of like process all of that Verilog code and add safe state logic to it. And that was probably like 3 weeks of work just getting that functioning. Kind of the same with the CPU implementations, because I was using the 68,000, like the FX 68K and one of the Z80 implementations, and none of those had safe state stuff built in. For the 68,000, I'm able to like capture its safe state just by triggering like an interrupt and getting it to running some custom code and getting it to just dump its state out to memory. But I wasn't able to do that with the Z80, so I had to like run that same script that I used for Hotego's code on the Z80 stuff. But for most of this, because I was building most of this stuff from scratch, it was I've like got a kind of like Verilog interface for easily hooking up save states to new systems that is pretty mature at this point. So I went into it knowing I wanted save states working, and I kind of built everything from that point onwards. So there was very few times where I didn't have functioning save states for this. So I would say for the PGM core, it wasn't a big deal. For the F2, it was kind of a big investment in time.
Yeah, but it was your first time doing that, right?
First time, and I think it's one of those things where like the payoff has been immense.
Yeah.
For the time investment was not insignificant, but the payoff for the time investment was well worth it.
Yeah, most probably you wouldn't be at the state that you are without that, right?
Yeah. Like it's the same with like the Pico ROMs. Like I don't know how many hours I've spent working on these circuits and trying to like cram all these like double-sided board down into this tiny form factor, and then like also wanting to sell it. So I'm like spending time like trying to make sure it's like foolproof, because there's things that I'm okay potentially breaking them myself, but I don't necessarily want people doing them. And like hours and hours of time invested in those, but like just the fact that like it would take 5 minutes to like pop a ROM out, put it in a programmer, erase it, reflash it, put it in and run
Yeah,
it, and now I can do that in 5 seconds instead of like 5 minutes.
it's friction, right? And
Yeah.
and that friction just destroys projects in the end. And also, it's not just that you can upload the ROM with your Pico ROM; you can view what's happening, right, in the bus with
Yeah.
your Pico ROM. That's amazing as well.
Yeah. Yeah. And like these are the kind of they change these things. They're not just like optimizations on how you work and like reducing frictions. They change how you think about problems and how you go about solving them. Like having save states is like it changes entirely how you think about solving some problem that someone reports to you. It's like, okay, just give me the save state and it will tell me exactly what's wrong, and all I have to do is look at it and work that out. So it's a very different. It changes how you work.
Yeah, yeah, and it also makes it an enjoyable experience, right?
Yes.
Because
Which it's important. Like some of this stuff is just like boring and tedious. Like it's not like every day you're like exploring and finding exciting new hardware features and discovering mysteries from 2 decades ago. Like sometimes it's just really tedious, boring work that's like soul crushing and you don't want to do it. And if you find ways to speed that up and make it more enjoyable, then you're more inclined to get more progress on these cores.
I guess this is general to all engineering, but I can only talk from software engineering and a very limited experience in hardware. Is that it's more fun to create the tools, right?
Mm-hmm. Yeah.
It's kind and you mentioned now about releasing the stuff for other users, and I made MD3 in a week, but it didn't have any polish. It took me 4 months to release it with an interface, with graphs, because it was just a bunch of numbers. And I said, this is unusable for anybody else but me, right?
Yeah.
And you have to polish everything, but that's kind of fun. You work on the barriers that you place on the like limit the stuff and make it user friendly, right? And what you
Yeah,
did with your Pico ROM.
yeah, like if I'm building something for myself, it's often like almost throwaway in how I think about it, and how like it would be unusable for almost anyone else to deal with because it's like a random Python script and some C code that I forgot how I compiled, and if in my mind I'm thinking about some other users who want to use these things, I approach it in a very different way than how
Yes.
I build it.
Isn't that, I don't know, I'm talking for by myself, if you're going to publish it, even though if nobody else is going to use it, but if you're going to place it on a public GitHub, it's a completely different thing, right?
Mm-hmm. Yeah.
You change how you write the code, and you end up doing that every time, right? But it does change when you know that people are gonna audit or at least look at the code.
Just even look at it.
Yeah, it changes completely. And Local Linux says, thank you so much, wickerwaka. Thank you, Martin. This is incredible for preservation, and it will transform the MiSTer into a .apache.io machine and make sure I never ever play anything else ever again.
I really like like these games are just so beautiful to me, and like I really didn't appreciate like these shooters, these cave shooters on this platform. Like I really wasn't aware of like how, first of all, how many of them there were on this system and how beloved they are, and they're a little bit intimidating. Like you hear like bullet hell shooters and you're like, okay, that's not for me. I don't know how to. I've seen videos. I'm not going to be able to play them. I'm going to die all the time. But they are like, I don't know. I'm growing in love with them as I've been playing them, and I'll never be like these people who make videos about them. I'll never be someone who like memorizes all these routes and all these different patterns. But like I can still appreciate the craft of these games and how beautiful they are.
Oh yeah, I do make videos about them. I'm literally terrible at them, but I love the way that they make me feel, right?
Yeah.
And I don't play on memorization. Of course, that does happen, but I don't push for that. I push for just survival. And yes, I know it's the incorrect way to play them, but they help me just like unwind and have a great relaxing time. People think that it's crazy to say they're relaxing. They are very relaxing because you keep your mind completely on the game, and that is something that many modern games don't accomplish, right? They are made so that you can be thinking about other things or be on your phone. And these games demand your attention, your emotions, and they bring you to a state where it's pure action, right?
Mhm.
And
Yeah.
it's kind of like meditation in some ways.
I really was surprised that I found them relaxing. Like I was just expecting them to be punishing and unfun if you weren't really, really good at them, and then just playing them and being like, wow, this is just, yeah, I'm dying, but like, man, that those 5 seconds where I just really felt in the flow and the music was hitting at the right time and just it just all clicked for those few moments is just kind of it's just amazing.
Yeah, and I'm really glad that you're sharing, helping, and making this possible for many people to be able to share this experience, not just now on the MiSTer, but also with documentation for the future, because that's something that I believe deserves to be preserved and pushed to future generations to be able to share them. And
Yeah.
this that you're doing is documentation work.
It is a little bit terrifying because it is a demanding audience who
Hmm.
knows extremely well how these things are supposed to behave. So like I feel like I have to push myself to a slightly higher standard than I'm used to.
Yeah, I completely understand, but it's better not to think about it. It's just like going into interviewing you. I didn't allow me to be nervous at all or anything. I just went into it and head on. It's kind of like the way that I found how to tackle problems is just to go into them, right?
I don't know why you would be nervous. That's ridiculous.
I don't know. Maybe I should. I was thinking about how I would react to this like 15 years ago, but now it's different, right? It's different now that you have some. I have some experience. You have some experience developing cores. That's kind of the parallel that I was trying to push. The experience in saying I'll define, okay, even if you don't know if that's for certain, but you know that you can do something.
It was like there was a when I did the IRM cores, they were kind of like, I don't know if I'll be able to do these.
Hmm.
Like it was just kind of like I can still remember the first time I got like an R-type Leo board, and I was like, okay, I'm going to sit down, I'm going to hook up a logic analyzer, and it will answer all the questions for me. And I plugged it in, and I just got this like essentially noise out of the system. I was like, oh my god, what am I doing? How am I going to like turn this into something actionable and understand what's going on? And like it was a long journey to like, okay, I can start piecing together a plan for how I'll do this, and I think I might be able to solve it, and I'll keep just moving forward. Um, and then when I did the F2 core, was more like I had the confidence of experience to know that like there wasn't really any problems here that I wouldn't be able to eventually overcome.
Hmm.
And like that core, there was a lot of different chips that had to be built on that core, but each one was just kind of like I just knew I just had to sit down and answer the questions, and then I'd be able to do it. And then with the PGM, it was kind of like at no point during the process was I was like, I don't know if I'll be able to do this. And it's not like I don't want that to come across as like arrogant or overconfident. It was just like I haven't had enough experience at this point that I felt like all these problems are solvable. You just need the right amount of time and find the questions you need to answer and focus on answering them, and then just move forward.
Yes.
Um, and it was kind of like a I guess kind of like the cave shooters. It was almost a relaxing experience, and like at no point was I was like, I don't know what I'm going to do. And it was almost kind of relaxing sometimes. Just come home and be like, these are the ABC. Here's the things I'm going to do this evening, and I'm going to make sure I make some progress so I feel good about it, and then I'm going to put it down. I'm going to come back to it tomorrow and do a little bit more.
Yeah, experience helps a lot. Like
Yeah.
it builds confidence. So what I was targeting for with that message is don't be afraid of tackling the problems.
Hmm.
Okay, and eventually, if you are uh, dedicated enough, you'll get out some results.
Yeah. Exactly.
Right, and Did you get the PGM hardware for this project, or did you have any from before?
I was just before we this morning I was just sitting down. I was like, when did I start on this? And like I started my first like code commit for the core is like uh in March of some point. And I bought a PGM on eBay on March. When was this order placed? March 10th. Um, and it arrived on March 19th. So I had no hardware until that point in time.
Mm.
And I think when the hardware arrived at like the kind of end of March, I had like basic like BIOS running in the core and doing some kind of correct rendering, but I knew it was not actually accurate to what the hardware was doing.
Mm.
And then once I got the hardware, and I'd also kind of like started writing some tests. So when the hardware arrived, it was then like, okay, well now I needed to build this thing so I could actually
Mm-hmm.
run software. I think I started building this when I ordered the hardware too. And then these got delivered, and then I have to spend some time debugging this and getting that working. Um, and I think probably by the end of March, I had something running on the hardware, and probably like a few weeks after that, I had like basic tile rendering was kind of the first thing I focused on getting working on the core. But it's really been like 3 months of
Wow.
work, I would say, which is a lot quicker than I thought it would all come together.
Yeah, it is. It's really quick. And you mentioned video. You mentioned the non-square pixels because the resolution is weird, right? It's 448 by 224, right?
Yeah.
And but you added some options because these PCBs were obviously for arcade monitors where you have the control on the H and P. I mean, it's not standard NTNC, neither resolution or frame rate, right?
Yeah.
So you had to do some things to be able to support users.
Yeah. So like it's Hotego built these like nice, super simple, like horizontal and vertical like position adjustment modules, which are really great for arcade cores on TVs because often they'll end up like over to the left or over to the right or like what. But one issue with the PGM is like on most monitors, um, even like the PVM I have behind me here, and like I've got
Mm-hmm.
a JVC D series over there, like the image was kind of squished like this way a little bit, um, and there was no real way to correct that unless you have some kind of like horizontal
Mm-hmm.
adjustment, like scale adjustment control on your TV. Um, so I added in because the core runs at has like a 50 megahertz clock is what the core itself is running at, and that gets divided down for various systems. Um, and the pixel clock is 10 megahertz. So it's an actual line is like 640 um, pixels across. So like the blank is like 100 and something pixels,
Mm-hmm.
and that's at 10 megahertz. So then I decided like I could probably do some scaling, like scale this thing up to like so you could stretch it a little bit on screen, like make the horizontal blank smaller and add some more pixels. But like if you're going from like 448 pixels and scaling that up to like maybe 480 to fill in that kind of like blank
Mm-hmm.
space on the screen, you're gonna get this very kind of like uneven scaling at those pixel sizes. It's not going to look super good. Um, so I added this mode where instead of running at 10 megahertz pixel clock, it actually runs at 50 megahertz. So the horizontal resolution is actually not like 448. It's 448 times 5, which is, I don't know, like 2000 or something.
Mm-hmm.
Um, and then you have all these pixels to play with. So you can I do some scaling in there, like slightly scale up from like, 444 to something. And because the pixel resolution is so high, like no TV can actually display like 2000, like no CRT
Mm-hmm.
TV. I won't say no because there are some really nice CRTs that can actually display that resolution, but your average consumer TV, um, isn't able to resolve like 2000 pixels. It just ends up like kind of blurring them.
Mm-hmm.
Um, and you just get this like genuinely surprisingly really good looking scaled up image.
Mm-hmm.
I was actually surprised at how good it looked when I implemented it and how simple it was to do. And I think it's one of my proudest features in the core, just because it's like it's pretty simple in its execution, um, and the result is so good. Like you can stretch this image, and normally you would expect to see some kind of like interpolation or some kind of like like jagginess or unevenness across the screen, and you really don't. It's like you got this like 5x pixel resolution that just kind of gets absorbed by the TV, and it just looks really nice. I'm super happy with how it turns out. Like you can't use it if you're using HDMI at the same time, but if you have a CRT TV, this scale just really gives you just enough flexibility to get the image to look really good on any TV.
That's awesome. And regarding the DAC, the DAC, the color, any problems with that?
I need to look into like what is coming out of that, and if it's the assumption right now is it's just like regular, you know, linear color coming out of
Most
there,
probably, yes.
but it could be doing something else. So something I need to look at and do some analysis on. Um, it's not like no one's come and said that the colors aren't correct. Um, the MiSTer kind of video pipeline itself is a little bit inaccurate in how
Mm-hmm.
it handles color anyways, especially when you get into the scaler and HDMI and where it applies gamma and stuff like that. But um, it would be interesting if there's something. I'm pretty sure all of the analog comes out of the video chip itself. I don't think there's any DACs
Yeah,
on.
that's what I'm saying. It's just resistors for the input, and that's that, right?
Yeah, yeah. So it's generating the sync and it's generating just the raw analog color.
Yeah, there's no
Um,
filtering.
yeah.
Probably
So
here? No, I don't know.
those are all kind of, I believe those are
The
all
bus?
pull-ups for the bus on
Yeah,
the card edge.
yeah. So there's nothing. It's
Yeah,
direct from the chip to the JAMA edge, right?
yeah. It's got as a system, it's kind of interesting how little like buffering and other things there are on the board. Like it's you can like I had this other board I built um, that I call the pass-through cartridge module. I call it a cartridge module. It's called PGM, but it's the idea of this was that it's just kind of like it's a PGM sized board, um, and with all of the signals broken out here. So then I can put the cartridge in here into it if I can force it in, and then I can plug this into the PGM, and then I can capture all of the signals that might be coming through through just this thing. So you can it's kind of like piggybacks onto another cartridge board. It doesn't work super great though because um, the the bus is very sensitive to noise
Hmm.
because there's no buffering on here. Everything is kind of just fed into everything else, and it's all managed by like chip selects on the chips. So and everything's running at pretty high clock speeds.
Yes.
So basically, building this what is essentially a giant antenna didn't work well with all those digital signals. So it was useful for some small cases, but not as useful as I hoped it would be.
I can't imagine what would be necessary to blind to just blind that signal, right?
Yeah, yeah.
Yeah. So anything else you want to share? Those are the questions that I had prepared. Uh,
I don't know. I feel like we've covered a lot. I don't know. I don't know what I'm going to do after this.
yeah.
People often ask me that, but I'm kind of
Yeah, I understand. That's why I didn't ask that because it's usually I'll know when I finish, right? But I was
yeah.
going to ask you something else. Do you feel compelled to port those scaling changes to any of your previous cores?
I might. I'd have to go back and look at them because it was really the motivation for doing it here was just that it was so kind of like
Needed, right?
yeah, it was just it wasn't even just like some CRTs had problems. It was like it was just every single
Mm-hmm.
CRT looked incorrect. Um, unless it had actual adjustments. So I'd have to go back and look at F2 and M92 and other cores and see like, would they benefit from this? It's a pretty simple change regardless. And Hotego's been talking about like maybe putting it on some of his cores too, because he has an H scale on certain cores of his, but it's just doing it. It's doing it at the kind of pixel level, and it looks kind of blocky in certain cases. And there was another developer who tried to get this merged into like the MiSTer framework, but it's a little bit invasive for that, I think, and it's very arcade specific. So
Yes.
I will probably go back and look at my other cores and see would they benefit from it.
Yeah. Does it make sense, right?
Yeah. There's a lot of stuff I want to go back to. I want to go back and take another look at M72 stuff. Like that was like my first core. I've learned a lot in the years since then, so I'd like to take a look at that. But it's also kind of, I don't know if you have this where when you're working on a project, like all of that information is in your brain and like your kind of like short-term cache memory, and then you go look at something you did 2 years ago and you're like, I have no idea who built this or how they did it, because it all just seems like Greek to me at this point. So whenever I go back and look at some of that old code, I'm like, wow, I really have no recollection of how this system works. And starting to work on it again is going to be like a week or two of just re-educating myself on all these things I used to know.
Yeah, it kind of happens. It happens a lot. Now, when you asked me about NV4E, I was like, oh, I have to go into that. Okay, let's go and check what that is. Of course, we always leave, where I try to leave that trail of cookies, so you can kind of rebuild it easier. But it's it's one of the reasons I didn't interview you for Taito F2. I was completely absorbed by other projects, and I didn't have the mind space to do it, right? And that happens. That happens a lot.
Yeah, I've gone back and looked at videos I have made or other people have made, simply because sometimes that's my only recollection of how some system worked. Is like, oh, I remember I talked about this 2 years ago.
It's like a dump, right?
It will remind me of it.
Yeah, hopefully this video helps you for that in the future. Yeah, so well, thank you very much for being here and talking about this incredible system and how the architecture works, and how the chips communicate. And I hope that you unveil I know that you will unveil the mysteries that are still left regarding the few games and the communication with the ARM processor that's left. Okay, and just thank you in the voice of the community, because you're bringing these games to a better level of preservation and access that they had before, and some exposition, because I believe that they are worth it, and your work is amazing for this. Thank you.
Thank you. I appreciate it. And thank you for being interested and providing a space for me to talk about this stuff. Like I really do, like, I do this for kind of just it interests me, and I find it exciting and rewarding to do. And like being able to share this stuff with people is like the most valuable part of it for me. Like if I was just doing this by myself with no one interested in it, I think I would quickly lose interest in it. But being able to bring games to people, being able to bring information to people is like the most rewarding part of this.
Yes, I bet. No, thank you. Thank you for doing it, and thank you for sharing it, and for taking the time to be with us here.
You got it.
Okay. Well, thanks very much, Martin. I hope to see you soon again, and I hope to meet in person someday as well.
Definitely.
Okay. Well, take care, and everybody, thanks for being around. Lobcodan Linux, Kokorito, Necromicoi, Hormoria, Olaf, all the people that have been around, and all the people that are going to watch this later on, because usually it's more in the reruns that people watch this stuff. I hope you enjoyed. If you have any questions, just leave them in the comments for us. And again, thanks, Martin, and I'll be waiting to play again these games in your course.
Thanks, man.
Take care. Bye-bye.